Welcome viewers to another episode of Space Science with Python. Last time we were talking about a NASA library called Spice and the Python wrapper SpicyPy that we were using to compute the position of the Earth and also Earth's velocity for a particular date, namely today. SpicyPy or Spice is a very mighty tool that allows us to compute like anything in the solar system. Positions, orientation, pointing, coordinates on surfaces of planets, and so on. And we will use all these tutorials to build up a certain fundament, a knowledge basis that we can use to create actual space science projects, to work on them, to derive scientific input. But first, we need to cover the basics and also to understand what we are doing actually. So I was being asked by some of you, what is the scope of all this? And well, the fundament is really important so that we can work on meteor data, on data from the Cassini spacecraft or Rosetta, or working on telescope data and so on. And if some of you may say, well, citizen science is, it's not really real science, it doesn't have any big impact or so, I really can disagree, because there is a study, the link is in the description, that shows that, well, in general or in mean, that citizen science papers or papers that have citizen science contributions are way more frequently cited than, let's say, regular science papers. Of course, this comparison is not very fair, because there are way more, let's say, science papers with pure academic contributions than citizen science contributions, and also if citizen science is also a little bit of marketing sometimes, but still the impact is huge, and this is also the goal that we are having here, so that at some point you are able to contribute something for the space scientific community. Now today we will still cover the Earth, and as the title says, we will take a look at the velocity and try to verify our results from last time. So here, this coding block from last time, I just summarized it, where we import SpicyPy, where we compute the date for today, or especially midnight. We import two Spice kernels that are needed for the time computation and also for the position computation of the Earth. We compute the ephemeris time by converting the UTC timestamp into this ephemeris time with the Spice function UTC to ET. And then we compute the state vector of the Earth, so the the six-dimensional vector that contains the positional information as well as the corresponding velocity information, together with the light time, so the time that the light needs to travel in the vacuum from the observer, in our case it's the sun, to our target, in this case it's the Earth. And you see we don't have the Earth or sun as names, but really integer IDs. And I just referred to the last time where we were talking about these NIF ID codes. Now everything was quite complicated. We were talking also a little bit about the reference frame. I would like to dive a little bit into this one today. And then we computed the state vector of the Earth for today. So I just did it for the 6th of October, so today, where we have the values in kilometers and the velocity in kilometer per second. So the velocity in kilometers per second for the X, in the X direction, Y direction, and Z direction. Now, first, before we dive into this data set and see whether this makes sense or not, let's have a small introduction into coordinate system. And well, today it's a very quick and dirty drawing. So what does it mean, ecliptic J2000? Now let's go here into the keynote and let's draw some things. Imagine you're looking from the top view down on the solar system. So on the solar system, we have, of course, in the center, the sun. And as you may know, the planets are revolving around the sun. We will next time, or in one of the couple in the future tutorials, we will see that it's not 100% true. The planets are revolving around the sun. So like the Earth here, you see we have the Earth revolving around the sun on some kind of elliptical orbit. So it's not a perfect circle, but really an an ellipse, so it revolves anti-clockwise as seen from the ecliptic North Pole. Now the ecliptic plane is a plane you can imagine that the Earth draws. So we have a table, the sun is in the center, the Earth is revolving around the sun on this table, and this table plane is the ecliptic plane. And all other planets are a little bit inclined with respect to this plane. They have their own plane, but our Earth is the reference plane in the solar system for us humans. Makes sense, right? And the coordinate system has a XYZ. XYZ is an XYZ system. You can create it with your so-called right hand rule. And what does it mean? Well, the x-axis points into the direction of the vernal equinox. So what does the vernal equinox mean? We take a look, we draw a line. Let's draw a white line, or let's make it gray. From the Earth to the sun in a gray color. And this is the x-axis. So really the x-axis of our coordinate system. And the sun's position here is now at the vernal equinox. So at the point where when spring begins. So the turning point between summer and between winter and spring. Now the z-axis points towards, well, us. So it's pointing from the screen into your face, into your direction. And the y-axis, of course, 90 degrees perpendicular, points into the other direction, namely here. So like something like this, right? And the z-axis and the z-axis again points towards you. Now this coordinate system doesn't revolve with the Earth. It's this coordinate system is steady state, let's say. So this is like the system we can also move now here to the sun, and from this coordinate system we can determine the positions everywhere. And that's pretty nice, right? And thinking now about positions and so on, keep this in mind, that this is the direction, again, this is the direction from the Earth to the sun at the springtime or beginning of spring, and that this coordinate system looks now like this. And it's steady state. It's not revolving or something. And that's basically it. So these are the coordinates. And let's take a look at the values. We can later go a little bit more into detail. We know that our Earth is approximately 1 AU from the has a distance of 1 AU from the sun, and 1 astronomical unit is 150 million kilometers. And you can see that the x value is almost 150, right? And the y value is like 32 million, so very small. And okay, z-axis, well, the Earth is more or less always on the ecliptic plane. So with respect to the reference frame of the year 2000. Now the point is, this value appears like strangely small. It's like it was 0 a few days ago or something. And it actually was. We can prove this. We will prove this in a second, because here at this position, the Earth started, well, for us in the northern hemisphere, spring started. Half a year later, the Earth revolves around the sun and is then in this position here on the top. And this is where the autumn time starts. So basically, the y value of the Earth at autumn is 0. Z is also 0, theoretically. And the x value of the position is exactly 1 AU, so at around 150 million kilometers. So you can compute it, use it as a small exercise, compute the time, not for today, but for the 22nd of September 2021. But we will get back to this in a moment. Now, another thing to prove that our code or the values make sense, we can work with the velocity of the Earth. So I just created a new Docker container. So the requirements txt contains now also NumPy and also matplotlib. So please do not forget to rebuild the entire container, right? And well, let's work with NumPy arrays. They are a little bit more easier to work with. So we use this one here. I already loaded all the kernels, so this should work. Out of the box, we can compute easily the distance from Earth to the Sun, and up distance, and we use the NumPy function linear algebra dot norm. So this is the Euclidean distance we can use to compute the distance. We use the first three values. Now let's have a quick look whether this is like around 150 million kilometers, as I just said, and we showed yesterday last time. Yeah, so 150 million kilometer. This makes sense. And now let's compute also a third value. Let's also compute the orbit velocity. So what is the velocity of the Earth that around the Sun in this coordinate system? And we do basically the same thing. We just use the last three values. So let's compute 3 dot, and that's it. And now we can print the orbital velocity. Again, in the GitHub repository that is also in the description, it's written with comments, and the print commands are a little bit more sophisticated. Now for the tutorial here, it's just to do some quick and dirty hacking and showing the results. And what is the result? Well, it's around 30 kilometers per second. So our planet, as we speak, moves around 30 kilometers around the Sun in the solar system. So now 30 kilometers, again 30 kilometers, again 30 kilometers, and so on. Well, it's quite fast, I would say. And the question is, to prove this, does it make sense? Is it really 30 kilometers per second or not? And thankfully, physics has a lot of equations and formula to work with. And also the equations are quite simple. So what we need, basically, we need the gravitational parameter, we need the mass of the Sun, and we need the distance between Earth and the Sun. Now, the mass of the Sun and the gravitational parameter, we can look them up at Wikipedia or somewhere else, but we will also use SPICE this time to have a common database, right? So if you share your code with others, they will have the same kernels, they will have the same values, or if you update your kernels, your values will have the most recent values stored, and it's way better than just Googling all the time and searching for the most recent value somewhere online. So we need another kernel first to load these parameters. And what is this kernel? Well, this is already part of the repository. We have it in the kernels again, so kernels, and then there's a PCK kernel which contains which has kernels like for physical parameters and so on. And there I downloaded a kernel that contains some of these values. Now again, you will ask, yeah, well, how do you know that it's this kernel? Well, again, it's years of documenting, of reading documentation and so on. So it's really it's really cumbersome sometimes to search in the documentation, but yeah, you can dive into it and find more things. Now there is a function that is called bot VCD, and this extracts information from SPICE. It returns you two values. Let's ignore the first one, but the second value is the gravitational parameter times the mass of the Sun, and it's really also in the corresponding units. And this one is called like this. We use spicy pie bot VCD, and this function says, okay, it requires a body ID. We need it from the Sun. What kind of item do we want to extract? It's the gravitational parameter times the mass. And how many dimensions does this value have? Well, 1. Why so complicated? Well, the point is you can also, for example, compute the radii of a planet. And if you ask, well, why the radii, not the radius? Well, planets are not like spheres, they're more like ellipsoids. So in this case, you expect 3 parameters to be returned. So the radius in x direction, y direction, and in z direction. And if your object is more complicated, you get way more results as well. Now let's compute the theoretical function of the velocity. So we just create a small lambda function where we say, okay, the g times m, so the gravitational parameter times the mass is one input, the distance between Earth and Sun, or some distance, and we will use the numpy math square, no, numpy square root, not numpy math, square root of g times m divided by the distance. And this is our function and provides us the velocity in kilometers per second. And since also the g times l value is returned in SI units, so no other units, everything is in kilometers, kilometers, in kilogram, and so on. So yeah, SPICE doesn't use meters, it uses kilometers. This is really important to know. Otherwise, your results will be messy. Now we compute the Earth orbit speed with respect orbit, like in the top you can see here. This one, we compute the velocity, but the theoretical expectations. So not the actual velocity, but the theoretical expectation based on the function we just defined. So we just copy paste it here, and we use the gm, so the gravitational parameter, times the mass of the sun. And since it's a list, not a float, we take the very first one, and it only has one dimension, as we indicate here. So this is the g times m parameter. And the second one is the distance, Earth-Sun distance, and we just computed it here and paste it here. And now we can also print our result afterwards. Again, I will just write some comments here so that you can understand it and learn by your own pace afterwards. Now let's print it. And there's an error. Well, this happens because it's spicy pie. And there's yet another error. This is, of course, very awkward. It's not BSP, it's TPC. And you can see this is real coding. You are debugging your code here live, so nothing really prepared. Yeah, spicy pie, not spice pie. I have to, I often forget that. Now, you can see our theoretical expectation is also around 30 kilometers per second. So this fits with what SPICE just returned, and this is pretty nice, I would say. So this is this for that. So the velocity makes sense. Now regarding the position, we said, okay, it probably makes also sense what we just saw, but let's go a little bit deeper into it. Let's really understand the data. Let's understand what we see there. So not just believing it, really understanding it. Again, we shouldn't be too obsessive with all these things, but I just want to give you an idea how you can verify the data. Now let's compute, or let's extract only the position of the Earth. So we use the state vector with respect to the sun, and we extract only the very three parameters of the vector, so x, y, and z. Not the orbit speed, but the Earth state vector. Yeah. So this is our position vector now, so just to simplify things. And now we will compute the position with respect to the sun, but normalize it. And you will just see in a moment why we are doing it. So I'm not doing it just for fun. I have, of course, something in my mind that I would like to show you how to work with it, and divide it by the Earth-Sun distance. So what we are doing, the guys that are fit in linear algebra, I mean, it's not very complicated, right? They know that we are normalizing the vector. So the length of this vector will be 1. So it's like 1 AU. Now, I just said here in this graph, let's have a reminder that the position of the Earth when autumn starts here is the X position is 1 AU, the Y value is 0, and the Z value is also 0. Now, a day later, moving here, so like a day later, the Earth moves with 30 kilometers per second. 1 day later, we have a certain angular distance between this autumn point and 1 day later. And a year has 365 days. The circle has 360 degrees. So let's just simplify these things. And let's say our Earth moves with around 1 degree per day, which means that the distance between the starting point of autumn and a day later is 1 degree. Now let's take a look at our calendar. We see that it's almost now not a week, it's I think now 2 weeks. Yeah, 2 weeks that passed the starting the autumn time. Now 2 weeks, yeah, it's like, let's say, I don't know the exact date, we are also computing midnight. Yeah, let's say something like, I don't know, like maybe 13 degrees or 12 degrees. This angular distance between the position of the Earth here at 1, 0, 0 and today. So let's compute this angular distance, and this is why also I normalize the vector, because what will I use to compute the angle? I will use the dot product. So the dot product is equal to the norm of two vectors times the cosinus of the angle. But since we are already normalizing our vectors, it's basically 1. So we just simplify these things. So what is the position of the Earth at, yeah, let's call it autumn, so normed at autumn? Well, it's simply 1, 0, 0. 1, 0, 0. So this is our second vector. Now let's see, did it work? It works. And now let's create a new cell where we compute the angular distance in degrees between the position of the Earth when autumn starts and now. So how do we do this? Well, we will use the r cos cosinus and compute the dot product, so np dot of this vector with respect to this vector here. Now the result is in radians, so we convert it into degrees. And let's make the formatting a little bit more fancier. And let's print the result. And the result should be like, yeah, something like 12 or 13 degrees. So hopefully this works and I don't have to redo the entire video because I embarrass myself. Invalid syntax. Now this is also coding in real time. Yep, there is something missing. Yeah, and we see it's 12.6 or 13 degrees. So also the angular distance makes sense between starting point of autumn and today. So not very surprisingly, it appears that SPICE returns values that we can work with. Now, SPICE is not the only tool. People wrote me, hey, there's Skyfield, there are other tools, SPICE is complicated and so on. And I know SPICE is it's very basic, but it's very important and extremely mighty, and it's being maintained by NASA, and it will be maintained for more decades, I'm very sure. And this SPICE toolkit is not only available for Python, there's also an online toolkit. So the next tutorial I would like to add, not really a new series or something, don't worry, we will cover programming and so on. But I would like to also show you sometimes some kind of online toolkits or other tools that we can work with to verify results, to get an idea, that visualize things in a more fancy way, to get a better feeling and understanding. So next time we will talk about a NASA online tool that helps us understanding the data even better. And then we will continue with more SPICE related programming. Now, if you have any questions about today's tutorial session, or if you have any feedback, please provide it to me. Write a comment or write me a DM either here or on Twitter. My Twitter account is also in the description. And I'm glad that you tuned in. I hope you learned something, and see you next time. Take care.